Hello and welcome to Appendix B of Chapter 1. In Chapter 1 we talk about the importance of units, and we're going to use units to actually write, not derive, the Maxwell relations in thermodynamics. Now there's a lot of YouTube videos where people show you how to derive the Maxwell relations from the thermodynamic potentials, the Gibbs free energy and the enthalpy and the internal energy, things like that. Or there are mnemonics which show you how to memorize the Maxwell relations using little tricks. We're not going to do any of that. We're simply going to write the Maxwell's relations, and we're going to be guided by our knowledge of units. So, there's no devices here. There's no field effect transistors or bipolar transistors. This is purely thermodynamics. So let's take a look at the Maxwell relations. There are 4 of them, and they involve 4 separate variables: the temperature, the volume, the pressure, and the entropy. And each of these these variables, has associated with it units. And here are the units of temperature. Let's start with the easiest one. The units of temperature are, well, we could measure it in degrees Celsius or degrees Fahrenheit. Generally in science, we measure it in kelvins, and kelvins has the symbol of K. The volume is measured in either cubic meters, or, since this is a semiconductor, of course, we measure it generally in cubic centimeters. Pressure is measured in force divided by square centimeters, and we'll keep with centimeters rather than meters. The units of force are newtons, so we have an N, which stands for newtons. Newtons per square centimeter. And last but not least, and we don't have to go into the deeper meaning of entropy, but the units of entropy are joules, energy per Kelvin. So a joule, or work, is force multiplied by distance. So 1 joule is actually 1 Newton meter, and we're going to be a little bit sloppy here and say instead of meter, we're going to use Newton centimeter. But the units work out, but of course this would be 100 times less than 1 joule. So this is 1/100th of a joule would be a Newton centimeter, because a joule is actually a Newton meter. But the important thing is that the units of entropy are Newton times distance divided by Kelvin. Okay, now here's the interesting thing. This really saves a lot of heartache. There's no velocity, there's no acceleration in any of this, there's no permittivity, there's no Coulomb, so that makes our task a lot easier. So the only thing that is going to guide us, the only real tool that we're going to use, is the fact that the units on the left side must be identical to the units on the right side. Let's check it out with the first relationship, number 1. So we have partial t respect to v, or t over v. So let's check the units of t over v. T, of course, is in Kelvin. V is in cubic centimeters. So we want to check and see if the units P over S also are in Kelvin per unit centimeter. Well, P is newtons per square centimeter. S is joules per Kelvin. And we just expand the joules now. So a joule is Newton centimeter per Kelvin. So the newtons cancel out. We have centimeter squared on the bottom and another centimeter squared on the bottom. So indeed it is Kelvin per cubic centimeter, exactly what we have for the units on the left side. So far, so good. Now, here's the thing one of the things which makes our life a lot easier. There's no such ratio of S divided by T or T divided by S that I can use on the left side, which has the same units of T divided by S on the right side. For example, here's the thing. You notice that if I'm using T and V on the left side, I can't use them on the right side. So TV here has PS over here. So if I had S over T, I would have to have P over V. Well, S over T would be, let's see, what would that be? S would be joules per Kelvin, and it would be divided by T, so it would be divided by K, and that would be joules per Kelvin squared. But there cannot be any joules per Kelvin squared, because if I have an S over T, I would have to have a P over V, and neither P nor V has a Kelvin in it. So the point is that I cannot have an S over T, nor can I have a T over S, nor can I have a P divided by V. There's no P's divided by V's in either of these, in any of the four of the relationships, because a P over V would be newtons divided by centimeters to the fifth. And there's no way that I can have a combination of S and T, which will give me newtons per centimeter to the fifth power. In fact, I'd have to have a Kelvin. So there can be no S over T, no T over S, no P over V, no V over P. Of course, I can have ST. ST is joules per Kelvin multiplied by Kelvin. That's a T, and that's joules. That's work. Same thing with PV. P is newtons per square centimeters. Volume is cubic centimeters. Newton centimeter, again, is joule, and that's units of work. So I can have the product of S and T, work, and I can have the product P and V, which is also work, but I cannot have their ratios. So that means that out of all the possibilities, I've taken away 4, and I've only got 8 left. Well, that doesn't make it all that trivial, but from 8 of these ratios, I can form 4 relations. And in fact, those relations are precisely the Maxwell relation. And here I've written out explicitly the 8 different relationships that are possible. I can start with any one, doesn't matter which one. I may as well start with A because that's the first one. This is completely random. Just write down P divided by S and ask what are the units. Well, the units of P divided by S are coulombs per cubic centimeter. And that's because P has the units of newtons per square centimeter, and S is joules per coulomb. That's down here. So this is the joules, and that's why I have the K up here because it's joules per Kelvin. Here is the units of P, which are newtons per square centimeter, so it's Kelvin per cubic centimeter. And then what I do, I've got 7 left. Where are they? They must be someplace. Oh, goodness. Oh, here they are. I just take a look, B, C, D, from B to H, and I ask myself, which of those has units of Kelvin per cubic centimeter? Now, I can try every one of them in order, but really what I'm looking for is something that has Kelvin on top. Well, this guy's got Kelvin on the bottom. No good. This guy's got Kelvin on the bottom. No good. This guy's got Kelvin on top. That's possible. And this guy's got Kelvin on top. So all these others, probably not that great. This one looks really good because it's got Kelvin divided by volume. So it's K for the T, and V is cubic centimeters, so it's Kelvin per cubic centimeters. So D looks like a pretty good choice. And in fact, that is precisely what we have. So let's go back and see if that indeed is one of our Maxwell's relations. Oh gosh, I forget which one was. P over S, T over V. Okay. P over S, T over V. So that's relationship number one. Now we'll figure out why these variables are held constant, and we'll also talk a little bit about the sign. But we've just done our first Maxwell relationship without using any thermodynamic potentials or any tricks, and it works out pretty easy. And now we only have 6 left to go, and here they are: 1, 2, 3, 4, 5, 6. And of course, you notice I've taken out D now. I've taken out A. That's the one I started with. I've taken out D. So here's the 6 left. May as well start with the next one. P over T. P is pressure, which is force per square centimeter, newtons per square centimeter. And of course, T is kelvins, so it's newtons per Kelvin square centimeter. Now I ask which of the 3 remaining, 5 remaining, not 3. Which one of these 5 have newtons per square centimeter Kelvin? So I've got Kelvin on the bottom. It's possible, but here it's cubic centimeters. Now, that's no good. Here I have Kelvin on top. Now, that's no good. Here I have Kelvin on the bottom. That's possible, but I don't have newtons. Let's see. Actually, I do, because S is joules, and joules contains newtons. So here, let's try S over V. Hey, if it's wrong, my bad, and I'll choose something else. But let's just for fun, because this looks promising. I've got Kelvin on the bottom, and I've got newtons on top. So if I look at S over V, it's going to be joules per Kelvin, and the volume is cubic centimeters. Joule is Newton centimeter, so it's Newton centimeter per Kelvin, and voila, P over T, S over V. P over T, here we go, P over T, S over V. So that's number 3. So I can eliminate 2 more. So now I've only got 4. So I have 2 Maxwell relation and 4 more left to go. Now again, let's choose next in line, which is S over P. And now I've only got 3 choices here. Entropy, which is joules per Kelvin, pressure, newtons per square centimeter, and of course the joule again is Newton centimeter, so it is newtons cancel out, cubic centimeters per Kelvin. Which one of these has cubic centimeters per Kelvin? It's pretty obvious. This is cubic centimeters, this is Kelvin, so it's V over T, and that is the 3rd relation. And of course, the 4th relation is what's ever left over, E equal to H. So let's see, we got S over P is V over T, S over P is V over T, that's number 4. And and that's it. And the 4th relation is just these guys here. T over P equals S over V. Okay, so we've been able to write all of the 4 Maxwell's relations in relatively straightforward manner. So let's go back and review, and I'm going to tell you that it's actually even easier than the procedure that we went through. There's another shortcut. We looked at one shortcut, which is once we have a Maxwell relationship in this form, we just flip it to get another one, which comes out immediately. However, let's go back, and I'm going to go through another shortcut. Okay, so let's go back to our first step. Just pick any one, doesn't matter which one. I happen to pick number A, P over S. Find the units. They are Kelvin. The Kelvin comes from the fact that entropy has Kelvin in the denominator, which means that Kelvin jumps up to the numerator, and the newtons cancel out in the denominator and the numerator, and we have a centimeter cubed in the denominator. So now we go to our step number 4, and we just have to match this guy with something on the right which has the same units. But there's a nice shortcut. Let's go back to the, right here, all four relationship. You have TV, PS, TP, VS, blah, 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 etc. Notice that on the left side, if we have T and V, there are no T's or V's on the right side. Here we have P and T, and we have no P or T on the right side. So whatever variables we have on the left side, those variables do not appear on the right side. And since there's only 4, we have only 2 choices. If we have T and V on the left, we can only have P and S on the right. So that eliminates a lot of choices. So instead of having 7 choices, in this particular case, we look only for those choices which have T and V. You know, V or S, that's out because it got a V. Here it's out because it's got a P, and this guy's out because it also has a P. There's only 2 choices. So instead of 7, there's only 2. Which one is the obvious one? Well, since Kelvin is on top, D is the obvious choice. So instead of taking, 30 seconds or a minute, this should take no more than 5 or 10 seconds. Okay, so it's really straightforward to write down the relationships. And now we have to deal with just 2 more issues. One is, what do we hold constant? Well, that's pretty straightforward because notice on the left side, in this particular relationship, we have T over V. We're wiggling V, we're changing V. And what are we holding constant? The variable on the right side. What's the variable on the right side? S. So if we see the S, this is the variable that we're wiggling on the right side, that's what we hold constant on the left side. And conversely, or continuing, if we hold wiggling S on the right side, that means that we hold V constant. So notice S, S, V, V, and that carries down for all of the relationships. Pick any one. Notice the P was wiggling on the right side, therefore P is constant on the left side, and we're wiggling T on the left side, therefore T is constant on the right side. So the picking of the variables which are held constant just pops right out of the Maxwell relationships. No thinking, no reasoning, no logic, just writing it down. And last but not least are the signs. So let's look at the signs. There are 4 relationships. Of course, we wrote them down hopefully relatively easily in only about a minute at the most. There are 2 that have minus signs and 2 that have plus signs. Nature is, again, very kind to us, because if you look at the ones that have the plus signs, they're kissing cousins. They're the ones that are flipped. T over P, P over T. And both of those have plus signs, of course, V over S, S over V. So these are the guys that have plus signs, and all we have to do is figure out why they have plus signs. And then when we figure that out, the other 2 will have minus signs. So let's try to reason out why these relationships have plus signs. And the easiest way to do that is to take a look at relation 3. Partial p respect to t, a constant v. Let's see why that is positive. Well, what it says is, at constant volume, if we raise the temperature, the pressure should increase. Exactly what we would expect, because the ideal gas equation tells us that PV equals nRT. So, if T goes up at constant volume, the pressure must go up. PV, V is constant, is equal to nRT. T goes up, P goes up. Think of it as a rigid balloon. If you raise the temperature, you're going to have an increased pressure. So as temperature goes up at constant volume, pressure goes up. This guy is positive. On the right side, at constant temperature, entropy is an extensive quantity. So if we double the volume, we double the entropy. So at constant temperature, as the volume goes up, the entropy goes up. So this guy is positive, and that's why there is a positive sign here. And you can use the same kind of reasoning, not quite as straightforward, but you can use the same kind of reasoning to show that this guy will have a positive sign, and if these two guys have positive signs, then the others have negative signs. And again, the reasoning, one can go through the same kind of logic to show that these must have negative signs. So there we have it. It should take perhaps only 1-2 minutes at the most to write down Maxwell relations using none of the thermodynamic potentials or mnemonics, just using units and some common sense. So I hope that's interesting, and if you find it enjoyable, let me know.